Good day, learners. Welcome to the GE 102 Geometric Geodesy. And today we're going to discuss the topic 3 of this course, which is all about geodetic positions and measurements in the reference ellipsoid part 2. So this will be for the authors and contributors of this material. And here is for the copyright notice. For the outline of this presentation, first is we're going to discuss the radii of curvature in the ellipsoid. Next is the length of the parallel arc. Next is the radii of spherical approximation to the Earth, or the mean radius of the Earth as a sphere. Next is the space rectangular coordinate system, or space rectangular coordinates. Next is we're going to discuss the curves on the surface of the ellipsoid. Next is the geodesic curve rather. And lastly is all about geometric reduction of measured directions, or azimuth. For the intended learning outcomes, after these lectures and exercises, you, the student, must have first is to illustrate and explain the concept of space rectangular coordinates in the reference ellipsoid. Next is to calculate space rectangular coordinates of points in and over an ellipsoid. Illustrate the concepts of radii of curvature, radii of spherical approximation, curves, and geodetic curves. Illustrate and explain the procedures and formulas for the determination of radii of curvature, radii of spherical approximation, curves, and geodesic curve. Next is to calculate radii of curvature, radii of spherical approximation, the curves, and geodesic curves based on a given examples. Next is to explain the concepts and importance of geometric reduction of measured directions, or azimuth, and distances to a reference ellipsoid. And lastly is to illustrate and explain the procedures of geometric reduction of measured directions, or azimuth, and distances to the reference ellipsoid. So we're going to start in the preliminaries to have a better visualization of our topic for today. So first is I'm going to let you imagine to have a pipe, no? So kaside naman siguro mo say pipe, no? So let's say this one, and we're going to have a red slide cutter na may kalawang na, no? So let us going to define what is curvature. So curvature is denoted with a letter K, small letter K. Now, so curvature refers to the rate of change of direction of the curve. Now, and a circle with a smaller radius has a greater curvature. Now, so as we have discussed earlier, that the smaller radius, no, or the as we illustrate a while ago from the previous slides, that as you can see that if the circle, no, if the circle now has a smaller radius, the rate of change is greater compared to the a circle with a much bigger, no, radius, no. So for illustration purposes, so as you can see, there is a circle with a small radius, no, and if you are going to visual check, no, the change of direction is mas paspas, no, mas dali siya mo change og direction compared nato for the higher radius with the other one. So so if you can see, no, though there is a change of direction na mas paspas, pero i-compare nato sa smaller radius, mas dako gid siya, no, of curvature. So we can say that a smaller radius has a greater curvature than the bigger one. So curvature formula is denoted with this again, no? Curvature is denoted with the small letter k, and here is for the formula. The second derivative of y over the 1 plus first derivative of y squared raised to the power of 3 halves. So this is the formula, general formula for curvature. So let's go to the first curvature, or the discussion of the radii of curvature on the ellipsoid. So first is we're going to consider a normal to the surface of the ellipsoid at the same point. When you say normal, that's 90 degrees, no, on the tangent point, no? So radius of curvature, the radius of the circle that touches the curve at a given point, that's the same tangent and curvature at that point. So lisod siya i-explain, no? So mo nang iyahang definition rather. So ato ang illustrate para mas dali nato siya masabtan. So let's say we have an ellipse here, no? Three-dimensional ellipse. And no, as you can see, there's a vertical line and there is a horizontal and another axis dimension. So this is the y, x, and z. And there is a point, no, on the surface, certain surface of the earth, kani si yellow. And when iyang pasabot, normal to the surface, no? When we say normal, we are going to make a 90 degrees, no? So this is the point mo na iyahang tangent line, and when we say normal, so 90 degrees sa iyahang tangent line. So the radius of curvature is denoted with the this Greek symbol, no? That's a phi, no? So si radius of curvature di ay class is just the reciprocal of the curvature. So kabaliktaran lang siya, no? Kabaliktaran. So ato itong i-reverse ang formula. So that's the formula for radius of curvature. So since ang ato ang formula haganin na is k for curvature, so reciprocal man, so 1 over k. So that's equal to phi. Mo na iyahang denotation. So basically ato lang gi-interchange ang iyahang formula. So we have now 1 plus first derivative squared of first derivative of y squared raised to the power of 3 halves over second derivative of y. So ato ang siyang dissect, no, ang formula. So since natay x, y, and z sa three-dimensional, so si first derivative of y is equal to dz over dx, no? And for the second derivative, so d squared z over dx squared. So first radius of curvature in the earth is what we call meridional section. So meridional section is a plane passing through the given point and the two poles, no? So dapat moagi siya sa North Pole and South Pole, no, ang iyang plane. And sa radius of curvature daw ay when you say class, no, so meridional section, it's just a plane, no, kung ato ang i-visualize na sa earth, ato siyang i-slice, no? So that's the section or the plane, no, ang katong mabuo niya nga plane. So that's meridional section. And the radius of curvature in the meridian is designated as m. So ato hunahon no, nasa earth ato siyang i-slice, no, and mupas dapat siya sa South Pole and North Pole. Then ang section or katong plane na makita nato pag atong i-slice, so that's the meridional section, but we are on to the radius of that section, no? Ang katurang radius ato ang at mas dito ta nato ibaling atong attention kay maoy ato ang need for curvature, no? Which is the radius of curvature in the meridian section. So that is designated by M. So for example, no? So balik tani kaganina sa ato ang illustration, there is a three-dimensional ellipse and there is a tangent line for this specific point. So let's say nga naamo dira nagtindog at the specific point of the earth. And normal daw, no? Normal siya from the point, no? Normal siya sa tangent line at that point, no? So this is now the radius of curvature. So first na radius of curvature is the radius of curvature of the meridional section. So ato sang i-visualize unsa na si meridional section. So atong i-slice, no, at that point, no, atong i-slice let's say that is the earth, no, kanya atong gibuhat karon na three-dimensional. So atong i-slice ang earth at that specific meridian kung asa ka nagtindog. Right, so tapos na siya slice. So katapos naman siya sa pikas nga face, so ato siyang ibalin sa pikas para ma-slice na food nato. Alright, so that's it. So as you can see, no, ato ang slice ang earth. Then let's see what's the outcome of this one if we're going to cut this out. Right, so tapos na siya. Then so mo na si point, and this is the ellipse. Then nara si point, no? Nara si point diri. Then ang radius of curvature is just this one, no? So kani siya. So that's 90 degrees, no? 90 degrees from the tangent line. So to have a better visualization to derive the formula for radius of meridional section is let's go back to this illustration, no? So this is the z-axis and this is for the x-axis, and that's the point kung asa ka na-locate or naka-station. Then we have here the tangent line. So that's and the normal of the tangent line is this one. So this is now the radius of curvature of the meridional section. And this angle is what we call latitude. So latitude, again, from our previous discussions and from the previous course, from your previous course, that it's from the latitude to the meridian, no? The line of the meridian of the location of the something on the surface of the earth. And if that's latitude denoted by omega, so this angle, no, in the outside of the triangle has the value of 90 plus latitude. So from our previous discussion, no, from the derivation of the x and y coordinates of the geocentric, geodetic, and many more. So we have this equation, no? So the derivative of z over x, so that's equal to negative cotangent theta. No, cotangents, okay, since z-axis is opposite man sa sine and adjacent is cosine, so that's cotangent, and cotangent is just equal to cosine over sine. No, cotangent na siya. Then we have also the second derivative if we're going to derive this one, no? This equation. So we have d squared z over dx squared, no, is equal to 1 over sine squared theta d theta over dx. But since our equation is in dx over d theta, so we need to dissect this one into this simpler equation. So 1 over sine squared theta is equals to reciprocal man, kay since we are going to have the dx over d theta, so we have 1 over dx over d theta. So muna siya, no, kay kanya tong gipangita sa atong equation. So next is we're going to recall the x coordinate of the geodetic latitude, no? Okay, since we are using geodetic latitude na sign, no? So we need to recall this one. So x coordinate is just equal to a cosine theta over 1 minus e squared sine squared theta raised to the power of 1/2. And using the quotient rule of differentiation, kung ato to siyang um, derive, no, using this quotient rule of differentiation, which is v du over dx minus u dv over dx over v squared. So that's the formula for quotient rule of differentiation. So if we're going to derive the x coordinate of the geodetic latitude, so we have this series of long derivations, no? And at the end, we can have this value of a times 1 minus e squared sine squared theta over 1 minus e squared sine squared theta raised to the power of 3 halves. So this is now the value of dx over d theta. So since let's go back to this equation ng atong giderive kaganina nga si d squared z over dx squared is equals to 1 over sine squared theta, d theta over dx is just equal to 1 over sine squared d theta times 1 over dx over d theta. So we're going to substitute this value that we have derived, no, from the x coordinate of geodetic latitude ato siya i-substitute diri as a dx over d theta. So we can now have the d squared z over dx squared that is equal to 1 minus e squared sine squared theta raised to the power of 3 half all over 1 times 1 minus e squared times sine cube theta. No, so we have this value na, no, sa second derivative of z over x. And we're going to substitute now, no, the values that we have, no, a while ago, which is the dz over dx. So nato nakuha ato nga negative cosine over sine theta. And si dz katong previous na to. Ang bag-o lang nato na derive. So d squared z over dx squared is mo ni siyang value. Mo na tong last nga gi-derive ka ganina. And we have also dz over dx that's equal to negative cosine theta and sine over sine theta. So these two values will now going to substitute in their specific variables of the formula for the radius of curvature. So the radius of the curvature in the meridional section now is this one na. No? Kung ato to siyang i-simpler form, ang atong gi-substitute ng mga values sa ganina sa first and second derivative, we can have this value. M is equals to a times 1 minus e squared all over 1 plus e squared sine squared theta raised to the power of 3 halves. So this is now the formula for meridional section. Next is the prime vertical section. So ganina is si meridional section, so karon na pod is si prime vertical section. So prime vertical section is a section through the point and perpendicular to the meridional section at a point, no? Perpendicular lang siya sa kadtong meridional section kaganina, no? So the radius of curvature in the prime vertical is designated as a big letter N. So si meridional is M, prime vertical is N. So let's go back to this illustration. So we have z-axis, z-axis, y-axis, and x-axis. And that's a three-dimensional. Then there's a point, no? And that's same point no atong illustrate ganina sa pagkuha sa meridional section. And we have this tangent line. And ang giyon ganina, the perpendicular to the meridional section. So ang ato na pong cutting line karon is ang kanina pong 90 degrees sa meridional section. So that's one. So we need to have we need to slice that one, no? Same sa atong gibuhat kay ganina. So we're going to slice that earth, no, to that specific plane, no. Then again, ang mabuuan na niya nga section, that's what we called prime vertical section. So tapos na niyog, then we can have now this radius, no, sa katong atong gikuha ganina. So the prime vertical section radius is the red one, and that angle is what we called geodetic latitude again. geodetic latitude. So for simpler illustration, no, kung atong himong two-dimensional, so this is normal or the prime vertical, no, prime vertical section kani siya katong nakuha nato kaganina. Then kaning from the point padulong diri as sa kaning line, no, sa z-axis. So that's what we call the prime vertical section radius, denoted as n. And from the angle from that horizontal, no, horizontal line going to the location or the point on where you're going to look, where you are located, no, where you are located is that's what we called geodetic latitude. And from the z-axis padulong sa point, no, kaning distance, so that is denoted as small letter p. So that's what we called as the radius of curvature of the parallel, ng parallel. So to get the formula for the prime vertical radius, let's recall with this illustration from our previous discussion from the part 1. So we have here geodetic latitude, and this is for the point or the location kung asa ka nakatindog. So ato na nag-discuss, no, from our previous presentation. And we have these geodetic coordinates. So balik ta, cx is equals to a cosine theta all over 1 minus e squared sine squared theta raised to the power of 1/2. So kung ato siyang i-differentiate, no, so ang NDI is from the point padulong diri asa kung asa siya nagka-intersect sa z-axis. So that's the normal prime vertical radius, no. So kani siya, kaning naka-red, so that's the n, no. And this is the geodetic latitude, geodetic coordinates, no, x geodetic coordinates. So therefore cx from this formula, no, x is equals to a cosine theta all over 1 minus e squared sine squared theta raised to the power of 1/2. So kuhaon lang nato si x, no. So kuhaon na to ang x, therefore si geodetic latitude di which is ang katong n, no, we can have the value of a over 1 minus e squared sine squared theta raised to the power of 1/2. Okay, since x coordinate from our illustration a while ago is, we can say that x is equals to n cosine geodetic latitude. So therefore si NDI is a over 1 minus e squared sine squared theta raised to the power of 1/2. Next is the radius of curvature in the prime vertical section is this formula. No. N is equals to a all over 1 minus e squared sine squared theta raised to the power of 1/2. So let's try to solve, no, the values of the certain geodetic latitude, no. At the equator, which is the geodetic latitude is equals to 0, so we can have the value for using the formula of meridional and prime vertical section radius, ha. So substituting the value of the geodetic latitude is equal to 0, we can have the m is equals to 633,503.4.50, while for n is 6378206.4. So how about if we're going to substitute the value of geodetic latitude into 15 degrees? So we can have the value of m is equals to 6339345.54, and for n is 6379652.88. And then at the poles, which is the latitude is equals to 90 degrees. So we can have the value of 6399902.55, and for n is 6399902.55. From the figure or from the illustration na atong gisolve karon, we can say that at the equator, no, the geodetic the prime vertical radius is equal to semi-major axis, and as the geodetic latitude changes, the value of m and n is also changes. No? And it is always that prime vertical radius is always greater than meridional section radius. So, mo ni siya ang mga facts about meridional section and prime vertical section. And at poles, no? At poles daw, si meridional section is equal to prime vertical radius. So, ato nang timaan ha. Then another curvature, no, nga aspect na ato i-consider for this lecture is the curvature of normal sections at any azimuth. No? So it says there that the maximum and minimum radius of curvature of any point P on the surface of an ellipsoid or rotation lie in the meridian and prime vertical planes. In some instances, geodetic computations require radius of curvature in a plane other than principal ones. And the normal section in the azimuth is denoted as alpha and has the radius of curvature at any point P designated as radius at alpha or RA. And the radius of curvature of normal section at any azimuth is solved using the Euler's theorem and is also called as Euler's radius of curvature. So this is the illustration, no? So si RA daw siya. RA. So we can have this formula, no? RA is equals to mn all over m sine squared alpha plus n cosine squared alpha. And facts about the radius of curvature at any azimuth is RA daw is equal to meridional section for normal section in azimuth 0 and 180. If you're going to substitute in azimuth of 0 and 180, so the radius of curvature at any azimuth will be equal to meridional section radius. And radius at any azimuth, no? Radius of curvature at any azimuth will be equal to prime vertical section radius for normal section in azimuth 90 and 270. If you're going to use that azimuth, then radius of curvature at any azimuth will be equal to prime vertical section radius. And at azimuth 30, 150, 210, and 330, the radius of the azimuth, no? Radius of curvature of any azimuth will be equal due to its symmetry. And the values of the radius of curvature at any azimuth will repeat mirror fashion with respect to both axes throughout all the quadrants of the section. And the values of radius of azimuth at radius of curvature at any azimuth will always be greater than m and smaller than n. So let's keep on remembering that, no? Mas dako siya compared kang m and smaller siya kang n. So another parameters for the radius of curvature is what we call the radius of the parallel. So from this illustration again, so we have the z-axis and the x-axis and the point of the location somewhere in the surface of the earth, and we have that the radius of prime vertical radius or the prime vertical section radius. So si n na siya. Then this is the geodetic latitude. So si radius of the parallel, from our discussion atong na-introduce naman ako ni ganina sa previous slide. So radius of the parallel is from the point of the location kung asa ka, then directly towards the z-axis. So kani siya nga naka-green. So that's the radius of the parallel. So that is denoted as a small letter p. Now, so the formula now is from our from the figure that we have discussed now from the previous slide. So we can say that the radius of the parallel is just equal to prime vertical radius cosine theta, no? Cosine geodetic latitude rather, where n is just this equation sa atong i-discuss kaganina, no? A is equals to 1 minus e squared sine squared theta raised to the power of 1/2. So next parameter is what we call the length of the parallel arc. So length of the parallel arc on an ellipsoid between 2 points having the longitudes 1 and longitudes 2. So if we have this longitude 1 no, of this certain location, and this is for the longitude 2, so the length of parallel arc is this one, no? So naka-more siya arc distance between two longitudes, no? That is denoted as big letter L. And the formula for the length of the parallel arc is just equal to prime vertical radius times the cosine theta and the change in longitude, no? Where n is again a over 1 minus e squared sine squared theta raised to the power of 1/2. Next is the radii of spherical approximation to the earth or mean radius of the earth as so as a preliminaries, no, in some application it is convenient to let the earth to be sphere rather than to be ellipsoid. So again, no, para mas better ang iyahang interpretation, no, or mas dali ang pag-derive sa mga formula, mathematical formula of our for this approximation, no. So gilet nila ang earth as a sphere rather than ellipsoid to avoid complications, no. It is necessary to find a suitable radius r of the sphere to be. So first radius is the Gaussian mean radius, no. So it is defined to be integral part or integral mean value of r taken over the azimuth varying from 0 to 360 degrees. So as again, no, integral mean man value, so iyaning integrate, no. So from this series of equations, nahimo na lang din siyang r is equal to meridional section radius times prime vertical radius section radius raised to the power of 1/2 or square root of mn. Another radius is the radius of the sphere having mean of the three semi-axes of the ellipsoid. Mean daw sa tulo ka axis. So since duha man ang sa atong ellipse, no, from 2-dimensional 3-dimensional rather, so namantay A and B, so that's the semi-major axis and semi-minor, no, axis. So denoted as RM, so which is the M as the mean, no, the radius of the sphere having the mean of 3 axes. So it's just equal to semi-major plus semi-major plus semi-minor divided by 3. Next radius is the radius of the sphere having the same area as ellipsoid, no, same area as ellipsoid. So surface area of the sphere, so let's recall, so we have 4 pi r squared, no, area, no, sa area ni sa sphere, no. And ang kanisya is ang surface area sa ellipsoid, so we have 2 pi times a squared times the quantity of 1 plus 1 minus e squared over 2e logarithmic function of 1 plus e over 1 minus e. So if we are going to manipulate these equations, no, into a simpler variables, no, and in terms of ra squared or the same area as the ellipsoid, we can have this a squared over 2 times the quantity of 1 plus 1 minus e squared over 2e times the logarithmic function of 1 plus e all over 1 minus e. No. And we have also the radius of the sphere having the same volume as ellipsoid. Kagaya na kay sa sphere area, kani siya is a volume. So the volume of the sphere is 4/3 pi times radius of the RV cube, no, or the radius of the specific sphere, no, and the volume of the ellipsoid is kani, no, so that's equal to 4/3 pi times a squared, which is the semi-major axis, and times b, no, which is the semi-minor axis. And ato na siyang equate, no, both sides, so we can have the value of the radius of radius of the sphere having the same volume of the ellipsoid. We can have this formula, no, the cube root of a squared times b, or the cube root of semi-major axis squared times the semi-minor. So alright, so much for the formula, no? We're going to go now for the example of those mathematical formula nga itong discuss na ganina. So using the WGS84 ellipsoid parameters, calculate the following. First is the meridional section radius at 60 degrees latitude, prime vertical section radius at 60 degrees latitude, the radius of curvature of normal section at any azimuth given the azimuth of 15 degrees, radius of the parallel at 75 degrees, length of the parallel arc of 45 degrees, latitude and longitude, and a longitude of 115 degrees. Next is the Gaussian mean radius. 7 is the radius of the sphere having the mean of the 3 semi-axes of the ellipsoid. 8 is spherical radius of sphere having the same area of ellipsoid. And lastly is the radius of the sphere having the same volume as ellipsoid. So first is we need to determine the parameters of WGS84. So we have A is equals to, or the semi-major axis is equals to 6378137 meters. And the inverse flattening is 298.257223.563. So to get the flattening of the WGS84 is just the reciprocal, no, for the formula of inverse flattening. So the flattening is now equal to 1/298.257223563. And since the formula of the flattening is semi-major axis minus semi-minor axis all over semi-major axis, is we can now determine the value of B, no? Okay, since na naman tayo flattening. So substitute the given variables, no? Flattening to be 1/298.257223563 and semi-major axis to be 6378137. So we can now have the value of B, which is 656,752.3142 meters. Next is to get the eccentricity. Eccentricity value of the formula for eccentricity is square root of a squared minus b squared all over a. So substitute the value, we can have the eccentricity to be 0.081821919093. For number 1, we need to get the prime vertical meridional section radius. So from this formula nga tong na-derive kaganina, so we can have m is equals to a times 1 minus e squared all over 1 minus e squared sine squared theta raised to the power of 3 halves. Substitute the given variables, then we can have the m to be 6383453.857 meters. Number 2 is the prime vertical radius. So we have the formula a all over 1 minus e squared sine squared theta raised to the power of 1/2. Now then substitute the given variables, we can have the prime vertical radius to be 6394209.174 meters. For number 3, no, plug and play lang ni siya class, no. Ang importante lang diri is dili ka mamali kay since all of the next questions, no, is prerequisite sa imong first nga gisolve. So pag mamali ka sa imong first nga gisolve, mali na dahil katanan, no? So for radius of the curvature at any azimuth is equals to mn all over m sine squared azimuth plus n cosine squared azimuth. Substitute the given variables ato ang question kaganina. We can have the radius at any azimuth is equals to 6384173.196. And for number 4 is the radius of the parallel. So this is the formula, n cosine geodetic latitude. Substitute the value of n and the latitude. We can have the value of radius of the parallel is to be 1654943.113 meters. For number 5 is the length of the parallel arc. So we have this formula n cosine geodetic latitude times the change in longitude. So L ang kinahanglan lang diri a class is if ever isa ra gihatag na geodetic longitude, you're going to assume that your first longitude is 0. Pero pag butang sa question nga na ay second longitude, then you're going to use it. And do not forget to convert the degrees into radian para makakuha kag answer. So substitute the value of n, the geodetic latitude, and the change in longitude. You can have the value of L to be 9075008.686 meters. Number 6 is the Gaussian mean radius. So it's just the square root of mn. So we can have r to be 6388829.252. Next radius is the mean of 3 axes. So a plus b divided by 3. So substitute sa a and b, you can have the value of 6371008.771. And for radius of the sphere having the same area in the ellipse is with this formula. Substitute the value of a and v eccentricity. You can have the value of RA to be 6371007.181. And lastly, for number 9 is the same volume of the ellipse, radius of the sphere having the same value of an ellipse, volume of an ellipse. So you can have this equation or formula, just the cube root of a squared times b. Substitute the value of a and b, you can have the value of radius to be 6371000.75 meters. So that's it for examples. Sayo na sa class, pero you need to be careful of your careful sa imong pag-solve kay since all of the questions are prerequisites from the previous one. So next that we are going to discuss is the space rectangular coordinates. So let's take a look in this illustration. So now we consider the computation of x, y, and z coordinates. So ang kalainan na sa space rectangular coordinate system class is we have now the value of h, which is the height from the height of the specific features in the surface of the earth with respect to the ellipsoid, or kanang gitawag na tog ellipsoidal height, which is h. And geometric or ellipsoidal height h above the reference ellipsoid. The geometric height is measured along the ellipsoidal normal. So kani si h. So this is the point in the surface of the earth, then si h is taman diri sa ellipsoid. So from this illustration, we have si x prime for this one, let's give it a pen color red. Okay, so si x prime, so this one is just equal to x, where si x is gikan sa kanino from the z-axis padulong sa kani. Ano siya? Mo ni si x, and we need to get the additional value, which is this one. So that is equal to since this is theta, so this is also theta, so therefore we can say that ang additional nga value, which is kani, is just equal to h cosine, since kay adjacent man cosine geodetic latitude. So next, or rather, since si n is from this one, color highlighter, so si n is from this one going there, this is n, n nga value, kani siya, si n na siya. So we can say that si x is just equal to kaning x, kani siya is just equals to n cosine geodetic latitude plus ang kaninga value, which is h cosine geodetic latitude. No? So that's equal to x prime. Okay, nara si n. And if we are going to look, no, at the above, no, from above, ani siya, atong ibutang atong I sa taas at North Pole. We can say this as this is the x-axis, and this is for the y-axis, and z-axis is padulong sa imuhang mata. No? And this is for the point, no? So kani si diri nga portion, or rather diri nga portion kaning nasa taas. So mao ni siya, no, si yellow. Nakadira nag-stand. So kaning blue equal na siya ani si x prime, no? Si x prime na siya. And this is for longitude. Longitude is kung from the prime meridian, no, which is at the x, no, we denote as ato na lang i-denote nga na ang zero meridian is naa sa x. So longitude is from the x, which is the zero meridian, padulong sa imuhang meridian, no? So that's longitude. And this one, see, this one is the x-axis, and this is for y-axis in terms of longitude. So from the space rectangular coordinates as seen in the figure nung atong nabuhat kani from this figure, no, we can say that si x, no, si x is just equal to, di ba kaning blue is mo ni siya si x prime, no, si x prime na siya. X prime is si x pala is just equal to x prime cosine longitude, since the value of the angle is in longitude. And for y is x prime, si x prime times the longitude, and si z is just equals to z prime. Later on ato na rin i-derive si z prime. Nara siya si z prime, ato na siyang kuhaon unya, no? So but no, dili man kita focus on the z prime, so we are more focused on the x and y, no, sa atong space rectangular coordinates. Pero ato dyan pong isolve si z. So using the equations, no, equation 1 and 2 nga itong na-derive ganina for x prime and z prime, we have, no, so mo na siya ang formula for x, no. Si x is just equals to n plus ellipsoidal height times cosine geodetic latitude times cosine longitude. And for y is we have n plus ellipsoidal height times cosine latitude rather sine longitude. And for z, no, which is atong nakuha ganina, so the value of it is came from the formula n times 1 minus e squared plus h times the sine of geodetic latitude, where si n is the prime vertical radius, prime vertical, which is a all over 1 plus e squared sine squared geodetic latitude times 1/2, raised to the power of 1/2 rather. So for each example, no, so using the Clark sphere 1986, which is the value is A to B, or the semi-major axis to be 6378206.4 and B is 6356583.8. We're going to calculate the space rectangular coordinates of this given latitude 13, 33, 41 and the longitude 121, 5203 and the ellipsoidal height of 25.6 meters. So let's try to solve for n first, no, kay since mao man ang pinaka gamit, no, for solving space rectangular. So n and c eccentricity rather, no, si n and eccentricity, but first we need to get the eccentricity because ang ato lang given is si semi-major and si semi-minor axis. So solving for eccentricity, which is the formula is square root of a squared minus b squared all over a. Substitute the variables, no, the given variables. We can have the value of eccentricity is 0.0822 7185422. As you can see, class, I am not rounding up, no? Dili ko mag-round up or round down, round off for the general term. Di ko mag-round off pag dili pa siya ang final answer ang gipangita. Okay, since maka-affect man siya, no, sa imuhang solutions. No? So for non-eccentricity, so next na to we're going to get is the prime vertical radius, which is the formula is a all over 1 minus e squared sine squared geodetic latitude times raised to the power of 1/2. No? Substitute the value of a and e and the geodetic latitude. We can have the given geodetic latitude. We can have the value of n, which is equal to 6379393.717 meters. So for x coordinate, we have this formula, n plus h times cosine geodetic latitude times cosine longitude. Substitute the value of n, nga ito na desolve ko ganina, and the given value of ellipsoidal height, and also the given geodetic latitude and geodetic longitude, or the lambda. We can have the value is of x to be negative 3274153.038 meters. For y, same mo sila og kanang formula ni x, but ang nagkalahi lang is si sine lambda or sa sine geodetic longitude. Substitute the value of n, the given h, given latitude and longitude. You can have the value of y to be 5266803.652 meters. And for z, no, the formula is n times 1 minus e squared plus ellipsoidal height times sine geodetic latitude. Substitute the value of n, the eccentricity, h, and the geodetic latitude. You can have the value of z to be 1485766.146. And for additional formulas, no, additional equations, so this is for review, no, sa inyo, ha. So si x is just equal to a cosine beta or parametric latitude, no, times cosine longitude. And for sphere, the value of x to be cosine geodetic latitude and cosine longitudes. Wala na siya a kay since di naman siya ellipse, no? Same naman ang iyang radius. And for y, no, for sphere is just equal to same lang yapon, cosine latitude and sine same ra siya sa katong space rectangular, but wala na siya a, wala po siya n kay since sphere naman siya. And for z is just equal to sine geodetic latitude, no, for sphere. So this is for additional learnings, no, or kamo na mag-solve kung given kung kinta sphere ang given, so of course ma-cancel man gyapon to siya kay wala man siya isa naman ang iyang radius, no? So I guess this is the last topic or the last part that we're going to discuss in this material for topic 3, part 2, which is the curves on the surface of the earth. So in this part, more on introduction lang ako ang ihatag kay since dili na siya compatible sa inyong part. So more on for masterals nani siya ng kanang magmasters na og Geodesy, no? Pero for your introduction purposes, I'm going to discuss with you. Alright, so when we say normal section, it is a curved formed by an intersection of a plane that contains the normal at a given point on the surface of the ellipsoid. So there are two types of normal section which we discussed a while ago, which is the prime vertical section and meridional section. So as you can see, it states here that intersection daw ko, no, of a plane that contains normal. When you say normal, that's 90 degrees from the surface or the point on the surface of the earth. So a specific normal section from point A to point B is 1 formed by intersection of a plane containing the normal to a point A and that passes through the point B with the surface of the reference of the ellipsoid. So, in the figure, we indicate that the normal section at point A to B, no, siya, A padulong sa B, and then B to A. So, nga na siya. Example na siya sa normal section. Noting that, in general, such sections are different because the normals of the ellipsoid at different latitudes intersect in the minor axis at different places. The two different sections are sometimes called counter-normal sections. Now, these different sections now nakita nato diri sa ato ang figure is sometimes what we call counter-normal sections. So here is a example of a normal sections in different surfaces of the earth. So this is only an introduction ng part. We're not going to deep in with this part sa pag-discuss. So this is an example of a separation between reciprocal normal sections. So this line is a normal section from A going to B, and the other one is the normal section from B to A. So dili na sila pwede mag kibali kung unsa tong normal to A to B, normal section A to B, does not also the same as the normal B to A. And there is also a separation between the two normal sections. So here's an example of a linear separation between reciprocal normal sections. And here is for the azimuth separation between reciprocal normal sections. And this one is the elliptic arc of normal sections. So the ellipse 1. And here is for the deep angle of the curve. So kani siya. Yan. So that's the deep angle of the curve. And here is also the normal section in a local coordinate system. So the kanakay siya denotations. So it's just only for introductions. So let's go to the geodesic curve, no? Geodesic curve, when we say geodesic curve, it is the curve which gives the shortest distance, no, on the surface of any between two points. No? If a surface is a plane, no, kung ang ato ang gamiton nga surface is flat lang siya, plain lang siya. So ang geodesic curve or geodesic line is a straight line. No? Straight siya basta syempre kung kanang let's say for example a rectangle surface. So ang shortest distance niya is a straight line na siya. Hindi na siya pwede mag-curve. And if the surface is a sphere or round, the geodesic is a great circle. Basta nakapamilya naman ang great circle, no? Sa inyong astronomy na subject or na topic, no? On the ellipsoid, the geodesic is a curve having double curvature and does not a plane curve. No, dapat dili siya plane curve. Same gyapon sa sphere. So sa ellipsoid, curve gyapon siya, dili siya plane. So this one, no? So normal section to A to B, kani siya. And this one is normal section from B to A, kani. This is A to B. So the geodesic curve is this one. Siya. And another definition for geodesic is geodesic or geodetic line, no? Between any two points on the surface of the ellipsoid is the unique surface curve between two points. Unique siya kay siya ra gyud ang pinaka shortest or shortest line, no? And at every point along geodesic, the principal radius of curvature vector is coincident with the normal to the ellipsoidal normal. And the geodesic between two points is the shortest surface distance between 2 points. The position of the geodesic with respect to the direct and inverse normal section is shown in the figure in the next slide. This one, So direct P1 to P2 and inverse pabalik na po siya P2 to P1. So this is the other normal, So therefore ang geodesic is this one. Kana siya. So there are many practical application of geodesic curve. So in the sphere, geodesics are used in the airline industry. So since the airplanes and airline companies and industries are using the most economical aspect, kung ato tayo mas prefer nila tong mas economical, mas dali, kasi since the earth is dynamic, so they need to strategize and to study more on where is the shortest route among the other choices to get in from the one country to another country, from nation to other nation. So specifically for spheres, these are used by the airline company. The concept of the geodesic curve in the sphere is being used by the airline industry. So kana makita ninyo sa ang track between the airplanes from different countries na adtuan nila. So they are using more on the geodesic curve na application and the knowledge of it. For long flights, for example, tag 16 hours na flight, inga na siya specifically inga na nga mga flights, they need to use the concept of the geodesic curve. The shortest distance between 2 points in the surface of the earth is not a straight line, So makita ninyo ang track sa kanang airplanes, dili siya directly na kanang kung asa tong mas doolog radius dito ang mas dito agihan, sa airline companies they are using this one, so dili siya straight line ang ilang ginagamit, but it is a geodesic curve line. There is not a line that is straight per se, but any of these lines are the shortest distance between 2 points on the surface of the earth. And the only line of latitude or parallels that is geodesic is the equator. So kung moagi ka sa equator, that is the shortest distance between if you are going to go to another places. So this is an example, So this one is the shortest distance if you are going to travel around the world. So in the sphere, geodesic curve are the most efficient, or the fastest and the most efficient routes to travel across the world. So mo ni siya ang pinaka the best na agihan nila, mo nang usually the airline companies are using this one. And this is also the easiest to understand example of the geodesic, kanang gitawag nato na efficient routes and the fastest routes to travel across the world. And on earth, these are the lines of longitude, the north or the north or south lines that run around the earth, as well as the equator. All the lines of longitude, as we all know, kanang from North Pole to South Pole. So that is all a geodesic, and for the latitude, only the equator. So this one, So all these from north to south, kada siya nga mga lines. So that's that line, tanan nga line are all geodesics, and for the latitude, only the equator. And in the ellipsoid na application, the earth, as we all know, is not a perfect sphere. We all know that because we are studying geodesy. So the routes that airlines taken can be modeled more accurately if we are going to use ellipsoid model. These are, of course, not completely correct because the plane will not be flying on the curve forever. Kung naisa ka destination, na certain time na mo travel na siya. And it also must take account no the wind and other physical effects as well. Syempre dili lang man jud pud pasabot na diya gid mo agihon ang diya gid niyo pagihon ang airplane tungod kay that is a geodesic line. Pero nadya po'y other aspects to be considered like winds and other physical effects na maka-affect no sa pag-travel sa airline industries. No? The flight path we look it's like a small section of a curve. So ang example daw ko no sa geodesic curve sa ellipsoid is a small section of the curve. So this one. So these are the geodesic line in the ellipse. This one. That is an example of a geodesic curve in the and in general, however, the planes will follow these curves to reach their destination in a timely manner. No, kanang mo nilang basihan nga okay in 16 hours makaabot ani nga location, in 15 hours and 10 hours, in 2 hours and so on. The difference between this and the sphere is that there is not a great circle. That there are not great circles. Okay, sa sphere, all the geodesic lines are great circles. But in ellipsoid, those geodesic curve are not great circles that go around the ellipse. In fact, some of the geodesic curves in the ellipsoid is mura siya og kuan, downright strange ang tawag. No, dili siya great circle. And this ellipse has more even deviation from the sphere, and this shows how interesting these curves can get. No, kung makita nimo ang mga geodesic curves sa ellipsoid na part, ma-amaze jud ka no. Kay syempre dili para sa sphere nga kuan siya great circle tanan. Right, so much for that. So I'm going to introduce also for further learnings no kung gusto pa jud mo explore more on the geodesy nga part, no? Especially sa geometric geometry. So there is a some aspect or derivation on the geometric reduction measured in the measured directions or azimuth. So mo ni iyahang equation. So you can also browse or study more about this one using this source na nasa ilalim na nasa to ang further learnings or references. And also the another same gihapon siya na formula which is same aspect which is also the geometric reduction of measured direction or azimuth, but we have also this another formula na pwede magamit. So since this was also an introduction, so you can read more of this one with this book no na nasa ilalim kani na nasa to ang list of references. Alright, so I guess it is the end of this slide for this lecture, no. If you have any questions and clarifications, feel free to ask in our FB page so that I can answer your questions and queries. That would be all, and thank you for listening. God bless and stay safe.